In this video, we continue to look at the basics of molecular orbital theory and derive expressions for the energy and the wave function. Let's look at the simplest molecule, H2+. It is a homonuclear diatomic molecule with just one electron. In a minimal basis, the molecular orbital can be approximated as a linear combination of two basis functions, or atomic orbitals, each centered on one of the two nuclei. Psi, the MO, equals C1 times phi1 plus C2 times phi2. The energy for this MO is E of C1 and C2 equals to C1 squared H11 plus 2 times C1 C2 H12 plus C2 squared H22, all divided by C1 squared S11 plus 2 C1 C2 S12 plus C2 squared S22, with the Hamiltonian matrix elements H and the overlap integrals S. Now let's apply the variational method to obtain the best approximation for the wave function. For this, we have to determine the values for the coefficients C1 and C2 that minimize the energy expression. Let's set the derivatives of the energy with respect to the two coefficients equal to 0. Delta E, delta C1 equals 0, and delta E, delta C2 equals 0. Carrying out the derivatives, we end up with two equations. C1 times H11 minus E S11 plus C2 times H12 minus E S12 equals 0. That's the first equation. And C1 H12 minus E times S12 plus C2 times H22 minus E times S22 equals 0. This is the second equation. This is a system of linear equations in C1 and C2. We can clearly solve it by setting both C1 and C2 to 0, but that's a useless solution. Non-zero solutions for the coefficients exist only if the so-called secular determinant is 0. The secular determinant is H11 minus E S11, H12 minus E S12, H12 minus E S12, and H22 minus E S22 laid out in a matrix format, and then the determinant of that. This is the secular determinant, has to be 0 for non-zero solutions for the coefficients to exist. Written out, this gives H11 minus E times S11 times H22 minus E times S22 minus H12 minus E S12 squared equals to 0. This is a quadratic equation for the energy, which can be solved easily. Once we have the energy E, we can go back into the linear system and solve for the coefficients C1 and C2. Let's look at the simplest case where the two nuclei are identical. Then, if the two nuclei are identical, H11 is equal to H22. Also, let's assume the basis functions are normalized. That is, S11 equals to S22 and equals to 1. Then, the solutions of the quadratic equation are E equals H11 plus minus H12 divided by 1 plus minus S12. And the coefficients are C1 equals to 1 over the square root of 2 plus 2 S12, and C2 equals to positive or negative C1. Let's actually write out the full solutions. The molecular orbitals are psi g equals to phi 1 plus phi 2 divided by the square root of 2 plus 2 S12, and psi u equals 2. And psi u equals to phi 1 minus phi 2, again divided by the square root of 2 minus 2 S12 here. The associated energies are Eg equals to H11 plus H12 divided by 1 plus S12, and Eu equals to H11 minus H12 divided by 1 minus S12. The subscripts G and U refer to the symmetry of the MOs with respect to spatial inversion. The first MO is called the bonding molecular orbital, and the second is the antibonding molecular orbital. Next, let's plot the energies of the atomic orbitals and the resulting molecular orbitals. The vertical axis is the orbital energy. We put the two AOs on the left and on the right, and the two MOs in the middle. This is called an MO diagram. For every MO, we draw lines to the AOs it is composed of. The bonding MO energy is lower than the atomic orbital energies, and the antibonding molecular orbital energy is higher. By putting the one electron from this molecule, H2+, into the lowest energy MO, which is the bonding one, we see that the energy is lower compared to the two separate atoms. Therefore, this molecule forms a chemical bond. In summary, we have seen that the variational method applied to molecular orbitals leads to a system of linear equations and a secular determinant, from which the energy and the linear combination coefficients can be determined. In general, two atomic orbitals give rise to two molecular orbitals. One is the bonding MO and is lower in energy, and the other one is the antibonding MO and is higher in energy than the original atomic orbitals. Using MO theory, we can explain the stability of chemical bonds.